Now let's continue with Module 3, Consequences of the Second Law. We're wanting to next look at reversible processes. The ideal process will be reversible. Now, that's ideal thermodynamically speaking. That's not practically what we really want. Now, there isn't a real process that is ever reversible, but we can approximate a real process as reversible if we take it really slowly and we always stay at near equilibrium. Now, this is why I say that this is thermodynamically speaking the ideal. Practically, I do not want my car engine operating very slowly and always near equilibrium. I'm never going to get anywhere. But I can do the best in terms of the energy conversion if I am operating reversibly. So slow, at equilibrium. What are the things that go wrong? Well, friction is the number one problem. Friction is unavoidable. Even in the best greased systems, I'm going to still have friction losses. I also have issues whenever I have unrestrained expansion. If I pop a balloon, I'm not going to get it back together. So that's going to be an irreversible process. Others that are going to be an issue for us and the problems we look at is really heat transfer through non-infinitesimal temperature differences. That's a problem. If I have water at the freezing point, liquid, and an ice cube at the freezing point, there's not a lot of change that has to happen. It could go either direction, either getting colder and freezing or getting warmer and melting. So that could be a reversible heat transfer process. But if I have an ice cube and I put it in a room of really hot air, it's going to melt. I am not going to get that ice cube back. There's not any tiny little change that would happen that would get it back. So when I have a temperature difference between my system and my surroundings, I have irreversible heat transfer. And another one that's not as big of an issue for us in this course where we're looking at pure materials, but is very critical when we get to looking at mixtures of chemicals, is the mixing problem. If I put things together and have them a well-mixed combination, I'm not going to get them back without a lot of effort. Now, let's talk about a thought experiment from the 1800s. Sadi Carnot, I guess French Revolution kind of times, had a lot of time to sit around thinking. And so he came up with this idea of what could be the ideal cycle. So first he started with a totally reversible isothermal, so constant temperature expansion at a temperature TH, where it gets the heat QH from that high temperature reservoir. So my system is going to absorb all this heat at TH and it's going to be totally reversible. Then I'm going to have this hot stuff and I'm going to expand it doing work. And this is going to lower the temperature from TH to TL, but it's going to be totally reversible, it's going to be adiabatic, and I'm going to expand the material and cool it. Then I'm going to go through another reversible heat transfer process, going to a low temperature reservoir this time, and now then I need to complete the cycle, so another reversible adiabatic compression cycle raising the temperature. So we're going to raise the temperature without adding any heat at this point. So this is a complete cycle. Everything about it is totally reversible. It's also totally impossible. But this is an important kicking off point for us because there are some observations that have been made. They are called propositions. Now, theories, a theory in science is something that has been observed time and time again to be true and has enough credibility that people believe it really is true, but it's still called a theory because we can't really prove that most of these things, there is no exception. A proposition is a lower standard than a theory. Okay? So these are propositions, but again, they still have not yet been found to be untrue. So, proposition 1. It's impossible to construct an engine that operates between two reservoirs that's more efficient than a reversible engine operating between those same two reservoirs. So the thermal efficiency of a reversible engine is always bigger than the thermal efficiency of a real engine. The next one of these says that an engine operating in a Carnot cycle between two constant temperature reservoirs, any engine that does that is always going to have the same thermal efficiency. So the thermal efficiency for a reversible engine is always just a function of those temperatures, the high and the low temperature. That's all that really matters. And then finally, a temperature scale can be defined that's independent of the properties of the substance used for measuring temperature. Now you have to remember that back a long time ago, they measured temperature and it was things like, the freezing point, the boiling point of water. But those change when you're under different pressures. They change if you aren't using water anymore, you're using salt water. So this is defining an absolute temperature scale, and I think we've all kind of come to accept that at this point in time, that seems to be correct. Now, if you take all of these things and play some math games, which we're not going to do at this stage in this course, what we find is that reversible ratio of heat transfers, the high and low temperature, is equal to the temperature ratio. If you take the absolute value of the Q's, it's equal to the temperature ratio. Remember, the temperatures are all positive. QH is going to be positive. QL will be negative in a heat engine. Just the opposite of that in a refrigerator. Thermal efficiency for a real engine, for any engine, is always going to be the power over the heat transfer N. For a reversible engine, we can use this ratio of the Q's is equal to the ratio of the T's and come up with 1 minus TL over TH. Now remember, this defined absolute temperature, so these must be absolute temperatures. And we can use the same absolute temperature ratio to talk about the coefficient of performance for refrigerators or heat pumps based on those formulas we had earlier. Now, comparing ideal and real machines. In cyclic devices, I always am going to be wanting to measure power over heat input. For a reversible engine, I can estimate it by 1 minus TL over TH. In an actual engine, it could be estimated by 1 minus the ratio of the QL over QH using absolute values. For a refrigerator, it's going to be turns into TL over TH minus TL for the coefficient of performance. Now this will not be limited to be between 0 and 1. This will be a number greater than 1. And an actual one was going to be QL over QH minus QL, and it's always less than that reversible coefficient of performance. Heat pump, similar formula. But all of these require that we use an absolute temperature for the T. Now we have another statement of the second law that is going to start introducing us to our next topic. So this statement of the second law is called the Inequality of Clausius. It says that whenever a system undergoes a complete cycle, so again with the cycles, the cycle integral of dq over t will be less than or equal to 0. So if you look at the net heat transfer divided by the temperature it occurred at, so if the temperature is changing along the way, this is going to be continually changing that temperature. But that sum over the course of the integral, some will be heat transfer in, some will be heat transfer out, but the sum of all of that is going to be negative or it's going to be 0. And this brings us to introducing entropy, which is a property of the system. Okay? Entropy is defined to be the change in heat over temperature when I have a reversible process. But the really cool thing about this is that this is based on an imaginary reversible process, but this is a property. It is valid regardless of the process. So we're going to imagine a reversible process to do our math, and then we're going to use it for our real processes. The units here will be heat units divided by temperature units, so a kilojoule per Kelvin, a BTU per degree R. Now this is going to have a basis because it's defined based on a change. So we don't have an arbitrary starting point that has a value of 0. So as long as we're going to be doing changes in S, it's not a problem, but there's not a this is entropy equal to 0 kind of place anywhere. We will be talking in the next lesson. I think I'm going to break here, and we'll be talking about how we can calculate entropy changes in the next lesson.